Hey guys, Buildzoid here, and we're still on the topic of Intel 13th gen, 14th gen degradation and instability issues. And I'm aware that Intel has now made a public statement of addressing this, and there's like a patch now, and you should install it right now, and there's going to be another patch in August. So, I like anyway. That's not what this video is supposed to be about. I'll look into that later. But what this video is going to be about is I had a really interesting conversation with somebody who runs Minecraft servers. And Minecraft servers are very single-threaded and very memory bottlenecked. So the 14900K is like the CPU for running Minecraft servers, except for the part where running Minecraft servers with 14900Ks rapidly destroys 14900Ks. Absolutely insanely fast. What I was told is out of 30, so this is a literal quote, out of 30 failures, all of them happened in 1 to 2 months. Ones running at 5.7 gigahertz are currently 3 to 4 months on average. So basically, what they're doing is because the failure rate was so insanely high, they've started disabling the thermal velocity boost on all of the CPUs running these Minecraft servers, because when the thermal velocity boost is turned on, I'll just pull up another quote. Running at 5.7 gigahertz still has CPUs fail, but instead of being like 30%, it's seemingly under 5%, like much lower and over longer periods of time. So yeah, basically on on the 6 gigahertz thermal velocity boost, they in like 1 to 2 months, 30% of CPUs would be dead. And so that's why they've started downclocking them now. In fact, the failure rate on these Minecraft servers is so high that the server that we're going to be taking a look at today, because I have a hardware info what's it called, report file from one of these failed blades. This blade currently doesn't have a replacement, which is really awkward, which is really unfortunate. But that data center no longer has replacement i9s to put into place, and they've stopped offering, because this is a commercial data center that this person is leasing blades in to run Minecraft servers on those blades. And yeah, that data center no longer offers i9 14900K based servers, because they literally don't have replacements, and the maintenance was just ridiculous, right? Because the maintenance cost of the you're not really expecting to be replacing CPUs every couple months. That's just not how that is supposed to work, right? Like every time you need to get a CPU replaced, there's a technician that needs to go into the data center, pull the blade out, this gets really expensive really, really fast. So basically, now the person leasing these 14900Ks, they have a year-long contract or something like that. So so they're still stuck on these, but the data center stopped offering new contracts for 14900Ks. And yeah, the blade we're looking at today is actually out of commission, degraded and getting replaced. Or the CPU is getting replaced. The blade itself is fine. Yeah, so these Minecraft servers have been absolutely chewing up 14900Ks, ridiculously fast. And they're not really anything particularly insane. It's this Supermicro blade. Like I mentioned, this is leased in a commercial data center. Now, Supermicro doesn't officially have the 14900K listed on their website here, but it does say that, if you want to run other CPUs, you can just contact them and they'll tell you if that is a good or bad idea. So I'm assuming that whoever built that data center probably got in touch with Supermicro, and they changed the cooling or something to support the 14900Ks. Not that that's a big deal. Because what I was told is that the max, this is another quote, the max temp these blades actually have hit is 83 degrees Celsius, usually run 50 to 60 degrees Celsius. So the thing is, Minecraft, because it's so memory bound, it really doesn't get the Minecraft servers, because they're so memory bound, they really don't get the CPU very hot, because they're constantly they're constantly doing memory access instead of this isn't like Cinebench, right, where you're running out of where it runs out of L3 cache and absolutely burns the cores to the ground. And another thing is, because these blades are running 128 gigs of low profile, ECC DDR5, they're running at DDR5 3600. They don't run like DDR5 4400 or 4000. No, this is straight up DDR5 3600, which is the Intel spec actually for 13th gen, 14th gen. Let me just pull up the memory stuff. Yeah. If you're running DDR5 and you're running 2 DIMMs in a dual rank configuration, 3600, which is what a 128 gig DDR5 configuration is. So, yeah, so like miserably low memory speeds, not really, like the CPUs really aren't running very hot, and yet these servers are burning, like this Minecraft server software is like burning through servers, like CPUs, at a rate of like 30% in 2 months, right? Just absolutely insane. So anyway, I figured I'd, let's first go through that hardware info report. So to see if like Supermicro is doing any of the wackiness that your Gigabytes and Asus and, the gaming motherboard manufacturers are doing. So yeah, we have a 14900K, 125 watt TDP. This is just, I don't think this actually affects anything in terms of operation. TDC 200 amps, so this is the board current limit, right? So there's sort of 2 current limits. Actually, there's like many current limits, but there's 2 main ones, right? You have the motherboard current limit, which on even like a mid-range or low-end Z790, I shouldn't say low-end because some of them can be kind of, but like a $200 Z790 motherboard will have a current limit so high that it really isn't relevant to this discussion here. But this is a like blade server board, right? This has like, I'm not even sure this is all V-Core. This might be a 7+1, but even if it was an 8-phase V-Core VRM, yeah, you don't really want to be putting much more than 200 amps through it. So this is the current limit of the motherboard itself. So if you run a extended load on the CPU, it will eventually, like, that load cannot exceed 200 amps because it would overheat the VRM, right? So there's literally like a hard 200 amp current limit on the CPU. Other than that, Supermicro is running the 253 watt power limit, which is Intel spec, right, for both PL1 and PL2. In practice, if you actually did run Cinebench all-core and, like, because the thing is, when these CPUs fail, the person leasing them actually, like, trying to diagnose the instability runs a whole bunch of stress tests. And he told me that basically when you try to do that, the CPU throttles down to, like, 165 watts. So the power limit isn't really relevant to this discussion, but yeah, it's not it's not unlimited like you see on your typical Z790 gaming boards. PL4 is 380 watts. I don't know what PL4 is supposed to be, but considering that both PL1 and 2 are following the Intel recommendations, I'm assuming this is also following Intel spec. TJ Max 100C, that's also Intel spec. That's just the standard TJ Max for any 13th gen or 14th gen CPU. And if we keep scrolling down, we get to our ICC Max. Now, on a lot of Z790 like gaming motherboards, this would actually not read out a current number. It would just read unlimited, because on 13th gen and 14th gen CPUs, you have there's a bit that you can flip, and if you flip that bit, you get it disables the current monitoring completely, so there's no current limit. Okay, it doesn't disable the current monitoring, but it disables the current limit, and when you do that, this just reads out unlimited. Otherwise, the actual range for the ICC Max register is up to 512 amps, or it's something weird like 511.75 something. It's not actually 512, but it's just under that. But anyway, so yeah, Supermicro isn't doing anything wacky there. This is what you would actually, what you see in the Intel documentation, right? This is a 125 watt CPU, right? 14900K, 125 watt CPU. 125 watt TDP. I shouldn't say the power consumption is a hell of a lot more than that, but, within the, within the wacky definition of what a thermal design power is, the 14900K is a 125 watt CPU. Even though it pulls way more than 125 watts, depending on what kind of configuration you're running it in, because, yeah, that makes sense. Anyway, 8P plus 16E, so right, 14900K, 307 amps. Yeah, so Supermicro literally is just following the Intel spec right there. Nothing to complain about. And then we just keep scrolling through and we get to the AC-DC load line. These are both set to 1.1 milliohms, which will, like, that just leads to very high voltages, just in general. But the thing is that is actually part of the Intel spec, okay? Like, if you scroll down here, maximum DC load line, maximum AC load line is 1.1 milliohms. And I've seen some people say, like, oh, well, if your motherboard, like, the reason this exists is because if your motherboard has, like, a bad voltage regulator, then you're going to need a very, like, deep load line slope so that the bad voltage regulator can keep up with the transient loading of the CPU. And it's like, yeah, that's true. And, like, this is a bad voltage regulator, right? Like, compared to what you get on, like, a Z790 gaming motherboard, this is, like, half the VRM that you get on, say, a Z790 Aorus Elite from Gigabyte. Or, man, I wish I knew Asus motherboard model names off the... Like, some Strix board is going to have twice as much VRM as this server, like, as this server board does, right? So within that whole, like, well, low-end motherboards should have droopier load line settings. Is this not a low-end motherboard? Would it be okay for, like, H610 boards to kill i9s? So yeah, I don't see that as an excuse, even though, like, I do realize that this leads to some significant, like, if this was 0 milliohms and this was 0 milliohms, the voltages would be lower. But, like, if Intel wanted these to be less than 1.1 milliohms, then the place to do that would be in the documentation, right? So yeah, like I don't, like, the thing is, like, basically what this would imply is that if you had a motherboard that had a really good voltage regulator, it has an unnecessarily large amount of V-droop, which is, like, okay, fair enough. Right? But that doesn't, like, prevent the motherboard from functioning correctly. And it shouldn't degrade the CPU, right? Because, like, the thing is, if you have a motherboard, and, like, there are some examples of this on older boards, for, like, I think Z390, and actually I think there's a few AM4 boards that let you do this, where you can set the load line slope way deeper than it needs to be. Oh, I think the Z390 Dark lets you do that, where, like, you have a bunch of load line calibration settings, and as you keep lowering, like, you obviously have the, like, 0 V-droop setting, and there's huge amounts of undershoot and overshoot, and then you have, like, 25%, and you know, now you get some V-droop, so there's somewhat less undershoot, somewhat less overshoot. And then by around, I think, 75%, you basically don't have any more measurable undershoot or overshoot, right? So the load line setting is now matched to the actual, like, impedance of the power delivery system. But that board lets you set the load line slope to, like, plus 150%. And if you set it to plus 150%, it doesn't give you more overshoot or more undershoot. It just gives you more V-droop. That doesn't do anything, right? Like, it doesn't help you from a stability perspective, but it doesn't cause, like, issues. I mean, other than the fact that if your core clock is too high relative to the amount of the voltage you're actually getting, you obviously won't be stable. But, like, so there's nothing fundamentally, like, wrong with a motherboard having a higher amount of V-droop than what it is than what its power delivery can do. Okay, like, that's not, like you're leaving, basically, you're not even really leaving anything on the table. From, like, I'm trying to think of, like, what consequences you have, and, like, the only issue you run into is, like, okay, your idle voltage is going to be higher than it needs to be, but, like, if the CPU is at safe voltages, right, if your CPU is safe on a potato motherboard that actually needs this amount of load line, then that same CPU is going to be just as safe on an amazing motherboard that can run half as much load line, right? So I really don't see this argument of, like, oh, the load line slopes should, like every motherboard should have its load line slope tuned specifically to its voltage regulator. Like, that would be a really cool thing if that was the case, because actually with the way Intel's boost system works on 13th gen, 14th gen, that would actually lead to slightly higher performance. That's the whole reason why you had a bunch of motherboard vendors intentionally setting the AC load line too low, which leads to instability even on brand new CPUs. Yeah, setting it to like the Intel recommended maximum, like either this is safe, right? And this is then safe on every motherboard, or this is not safe, and this isn't safe on any motherboard either. Right? Like there's no like and like basically you're like leaving performance on the table. You're not leaving reliability on the table by having this at 1.1 milliohms if Intel actually did their job with specifying this correctly. Now then. Yeah, so within my understanding of how Intel power delivery works, this is fine. And as far as I know, the new patch from Intel actually just like forces all motherboards to this anyway. So like, I don't think my understanding of Intel's power delivery is wrong here. This is like, if your motherboard sucks, like you aren't allowed to design a motherboard that requires a load line slope higher than this. If you design a motherboard that can function correctly with a load line slope lower than this, that's great, but you're not forced to use a lower load line slope than this that we see here. But either way, this is kind of, I mean, actually from a powered, like voltage regulation wise, this could actually work quite well. Then again, there's probably a whole bunch of signal traces running direct, like under the voltage regulator, so that might be kind of complicated. Actually, they're probably sneaking them around the side here. I'm not actually sure how this, unless this is all power over here. I'm not sure. But anyway, because the thing is, when you actually have the voltage regulator, like, really, actually, it's not real. I'm not mistaken. Yeah, the power delivery pins are all sort of over here. So this being over here is probably not ideal. Because you're just going to have, like, the distance the current has to travel leads to more voltage drop, like, you get more resistance, more inductance. Those are both, you know, bad for your, like, load line, effectively. Anyway, but yeah, so this is not some miracle of power delivery, so it kind of makes sense that, honestly, it might actually require a load line slope of 1.1 milliohms. Now then, so, yeah, so basically from with my understanding of Intel's documentation and their power delivery, this looks fine. I don't see anything wrong with this. With, like, what Supermicro has put onto this board out of the box. Like, I don't see anything that would immediately, like, I don't see anything here that's like, oh yeah, this is going to cause the CPU to degrade. Right? At least if I'm to trust Intel's documentation. Now, if I said, hey, that 1.1 milliohm load line is going to cause the CPU to degrade, then that also means this right here in Intel's own documentation will cause the CPU to degrade. Though, on that note, actually, you know what? We'll get to that soon enough. So, basically, from what I can see in the hardware info report, this is as close to, like, Intel spec as it gets for a motherboard, as far as I can tell. I could be wrong about that. But this is still way less, you know, like if this was a Gigabyte board, your power limits would be set to like 4,000 watts or actually, no, that's an Asus thing. Gigabyte usually set one of them to 280 and the other one to 4,000. I think it was like 4,000 on this, and this would be set to 280. So, yeah, so Gigabyte would like blow up one of them, set the other one to 280, and they would disable the current limit. The AC load line would be at 0.4, the DC load line would be at 0.9. The end result was that if your CPU didn't win the silicon lottery when you bought it at the store, you could put your brand new, healthy, you know, factory sealed CPU into your Gigabyte motherboard, and you wouldn't be able to run Cinebench because the CPU would think that, like, because the load line slope that the motherboard was reporting to the CPU was actually significantly lower than the load line slope that the motherboard's voltage regulator is actually using. The end result was that the CPU would make voltage requests assuming that it would get a lot more voltage than it was actually, like, expecting to get a certain level of voltage, and then it would get significantly less than that, and it would crash. Also, in order to be able to lie to the CPU about the voltages like this, Gigabyte disabled the CEP, because if CEP is turned on and you mess with the AC load line like what Gigabyte was doing, CEP gets very upset and clock stretches the CPU to the point that you lose like 50% of your performance. So, however, it will be stable in that scenario. It won't crash if it's clock stretching that hard. So yeah, basically, as far as I can tell from, like, Supermicro isn't really doing anything wrong here. At least within my limited understanding of Intel's documentation. Now then, let's take a look at some interesting screenshots from this system, because, of course, the question, like, the thing I was wondering about was, like, okay, so if you're running single-threaded Cinebench, right, which, admittedly, is not a Minecraft server, what kind of voltages does the CPU get? And unfortunately, we do not know. We have vid requests, right? We have core vids over here from Hardware Info, but unfortunately, this motherboard, I didn't have a way to get core voltage readings directly from the voltage regulator, so we don't actually know what voltage the CPU is getting. And this annoys me even more, this motherboard doesn't even have a core voltage sensor on the socket. Okay, like, this is pretty standard practice for a lot of motherboards, that you'll have the Super I/O chip will have a core voltage sensor that's just somewhere on the V-core power plane. And that one usually is somewhere vaguely near the CPU socket, you know, like sometimes it's in the middle of the socket, sometimes it might be a little bit before the socket. If the manufacturer is feeling especially stupid about where they position that sensor, they'll put it like right off of the inductors, and then it'll read insanely high voltages that are not accurate at all. But usually, like, if it's sitting somewhat near to the CPU socket, it'll actually read it won't be super accurate at high current loads, but at low current loads, it'll actually give you a pretty good idea of what actual voltage the CPU is getting. Unfortunately, we have absolutely no such voltage readings for this motherboard whatsoever, and so that is annoying. However, we do have vid requests, and within my understanding of Intel's power delivery system, the CPU here is reporting a current draw of 50 amps, and the vid request is like 1.4, like it's between 1.44 volts, and it occasionally went up to like 1.54. So at 50 amps with that 1.1 milliohm load line, I'm going to assume, you know, we're seeing like 50 millivolts of V-droop. So the actual voltage at the CPU is probably somewhere between 1.4 and 1.5 volts. It's not actually reaching 1.55. Now, I also don't really think 1.5 volts is safe for the CPU, just generally speaking. Yeah, that, like I don't have evidence for that, but that is currently my suspicion, is that the reason we see so many i9s failing is because a lot of them have a literal vid, like their max vid for 6 gigahertz is like 1.5 volts or close to 1.5 volts. And then when you're not loading the CPU very hard, it runs at that insane voltage and degrades. But anyway, so yeah, so this is doing basically typical 14900K things in terms of core voltage requests when running Cinebench. So that's not too surprising. It's worth noting that, like, temperatures are fine, right? Like, we're 74 degrees, 66 degrees Celsius, like right now. So yeah, it's not, you know, it's not perfectly flat, but it's not running super hot in this like single-threaded workload. And also, in a single-threaded workload like Cinebench, it's only pulling like 60 watts, right? Like, it's really not pulling a lot of power. That package power reading doesn't really make sense. How is it pulling 50 watts at 40, like at almost 50 amps while requesting 1.5 volts? Does this board have broken current sensing? I mean, we do have VCC power out over here at 64. That seems more accurate, but like, VR VCC current. IA core power. I mean, I guess that might not include the ring power? Because the funny thing about software power readings is they're only as accurate as the power measuring, like, as the power measurements delivered by the hardware. And sometimes they're really inaccurate. Yeah, like there are boards out there where the power readings are off by like 10, 20%. Which shouldn't cause degradation, but is not ideal. Let's just put it that way. Like if you design your silicon with enough safety margin, your stuff shouldn't degrade because a power reading is off by 10% or 20%. Anyway, yeah. So like this is doing the typical, 14th gen single core workload, extremely high voltage stuff that you see from basically any 14th gen system. Also, I actually have a screenshot of even higher vids. Unfortunately, that one doesn't include all the lovely information about like what the system actually is. It's just a lonely vid readout because the system crashed while doing this. Because yeah, this 14900K is very degraded. Which is why I got this opportunity to get some tests and get some data off of it, because otherwise it would be running Minecraft, but it's too degraded to run Minecraft anymore, so it gets to be featured on my YouTube channel. So yeah, so this is how a server board like this behaves, and also yeah, it's not hitting the power limit. And when it's running Minecraft server software, it's not hitting the power limit. It's not running super hot, right? Again, I'm just gonna read that quote again. The max temp these blades actually have hit is 83 degrees Celsius. Usually run 50 to 60 degrees Celsius. So these things, they're not running super hot, they're not hitting the power limit, and they're degrading really, really fast. Now, if you look at I have this lovely graph of the player numbers on one of these blades. I don't think it's this specific one. Of what it looks like when one of these gives up, right? So the server gets restarted every 24 hours. That's why on every date indicator here, you can see that big dip in player numbers. That's the server getting periodically restarted. And then we have some networking outages. And then over here, we get our first hardware failure, right? So it goes down. Oh, actually, it's just, yeah, we just have this massive, in the middle over here, it goes down. Then it gets restarted, seemingly goes down again. Then it gets restarted. So it seems to be fine now. Restarted again. Then it goes down randomly. Then it's restarted. Then it goes down again. Then it gets restarted, and it doesn't want to get back up anymore. Right? And actually, there's a closer view of that. So yeah, you can see here where it's that's that first failure. And then we have that periodic restart. Yeah, it has some issues over here. It actually kind of looks like it starts up, or it dies, starts up, kind of dies again maybe. The thing is the CPUs, when they start degrading, they start spitting out memory errors and stuff, right? So the software might actually be trying to recover in this situation, but it's having issues or something. And then yeah, we have another regular restart. Then it runs fine for a few days, right? There's no crashes here, no crashes there. Here it dies, gets restarted, dies, gets restarted, and then it's just over. At this point, it can no longer run Minecraft. Yeah, so this is what it looks like when one of these servers actually goes down over time. Oh, and then you can see, yeah, the machine got replaced, and the monitoring broke. And so yeah, and now, the main difference I can think of with, why... Because it's, I don't think we've heard anybody, or, I haven't heard of many reports from people where it's oh, my CPU, massively degraded in, 1 or 2 months, right? Most of the reports have been, multiple month usage before, issues. Though, sorry about that. Though, I guess part of that could be that a lot of regular, desktop users might just not expect their machine to be super stable. Right? Oh, my, browser crashed. Oh, my driver crashed. Oh, I getting GPU errors, right? And it's and that's the thing is, when the CPU, for most people, I think, their main experience of this, the degradation and the instability is that, oh, the shader compilation crashed, or decompression for some game crashed, right? So it looks like a GPU issue a lot of the time because the CPU is preparing all this information to give it to the GPU, and the CPU screws up the decompression, and the GPU gets very upset over this jumbled mess that the CPU hands over, and it's like, there's your decompressed textures, and it's like, this is not, the GPU's like, but this is not a texture, crash. So that could be part of why we've not, like, I'm not aware of, like, reports from people where it's like, oh yeah, my CPU just goes from, like, perfectly functioning to, like, completely unusable in, like, 1 or 2 months. But my other suspicion is that most people probably run their CPU harder than these Minecraft servers get run, and they don't run them literally in the same workload for 24/7, right? Like, because again, the main fix that the person leasing these machines has had for this, like, rapid deterioration of these servers is to just disable TVB. And they do that from the operating system. They don't even go into the into the BIOS, because this is a super micro BIOS. There's nothing there. You can't change anything. You can, like, disable eCores and you can disable hyperthreading, and that's it. So what they've been doing is literally just telling, like, in the operating system, limiting the maximum boost state. Because you can't go into the BIOS to change anything. Yeah, so basically, and so they're literally just turning off, like, the 6 gigahertz boost, right? And that drastically improves the endurance of the, the endurance of these servers. And so I suspect what the issue here is like, most people don't run a workload where, you know, you're running 24/7 on boost, right? Because your typical AAA game these days will use more than 2 cores. If you have a browser open in the background, right? If Windows is doing stuff in the background, if there's, like, basically anything else running on the system, you're probably not hitting TVB. Whereas, and also another thing about this Minecraft server software is it really hammers the memory system. So it probably puts a lot more stress on, like, the ring and the memory controller than what your typical daily user would see. So that's kind of my suspicions on why these seem to just, like, that's sort of like my suspicions about why it seems to be that this, like, running Minecraft servers just absolutely wrecks i9s. Is, like, it's probably because this is actually a very light load at just constant usage, right? This isn't, like, they're not rendering videos on these. They're not, you know, compressing large files. Like, this is running a Minecraft server. This really isn't heavy. The machines aren't hitting the power limit. They're not hitting the temp limit. They're, right, like, they're really not hitting any of the usual, like, oh, my CPU is hitting 100 degrees type stuff. Like, that's not happening. And yet they degrade incredibly fast. And what I also found really interesting from the person leasing these systems is they told me the following, and this is another quote: all of these CPUs pass all core workloads. Every single one. LinPack, Cinebench, Prime 95, Y-Cruncher. It usually the prime cores degrading in particular. So by that they mean, like, if you look in hardware info, it'll be like core 1, 3, 5, 7, and 9. Oh wait, it wouldn't be 9. 9 is a E-core. But yeah, so apparently the prime cores degrade more often than the even cores, which is weird. I don't know if that, like, it might be due to where they're positioned on the ring or something. I kind of wonder if all of the prime cores are on the same side of the ring. But yeah, I don't know. So that's just, like, an observation that they've had. I also, continuing the quote, I have had an E-core cluster just randomly die. So that's interesting. And this is, like, these, like, random, like, E-core cluster failures is why I've been suspicious that this isn't the cores themselves falling apart, it's the ring. And the thing is, when the ring breaks, well, all of the cores, like, the ring is the interconnect between all of the cores and the L3 cache, right? The L3 cache kind of acts as the interconnect between the cores. You want to pass information from one core to another, you put that information into the L3 cache, and then the other core can access that information in the L3 cache. Bam, right? And the thing is, like, so that's sort of why I've been wondering is, like, is it just the ring falling apart? Because if the ring is degrading, it's going to cause random other parts of the chip to break, even if they're not really very stressed, right? And the E-cores really, like, they're clocked super low. They don't run super hot. They do still see the same insane voltages that the Ring and the P-cores see because they all share the same voltage rail. But, like, they really shouldn't be failing. Like, that doesn't, like, just, you know. So that's, and the thing is, when the Ring breaks, it'll look like the cores break because if, let's say, the Ring stops being good, like, reliably able to hand over data to the cores at high frequencies or at high load, then, like, you'll have a core boosting to 6 gigahertz and it's pulling garbage out of the L3 cache or something like that. Right? So then it looks like, oh, that core has failed, when actually it's just its ability to access the Ring has fallen apart. Or something like that. Like, again, this is just speculation on my part to try explain, like, why would the E-cores fail? Unless, like, everything is super fragile and it actually just doesn't matter what's getting loaded. But I would suspect, like, all of the failures would probably have, like, a common... Like, all of the degradation would have, like, a common component that the degradation is affecting primarily. And it's not just, like, random parts of the CPU failing at random. Just because of, like... operating voltage, basically. Because I think in this case, right, again, like these servers usually, like, again, that quote, usually run at 50 to 60 degrees. Like, I don't think if the server is usually running at 50 to 60 degrees that you can say operating temperatures are the reason why this thing is degrading, and it's voltage, right? Like, something somewhere in that CPU really isn't liking the voltages that it's getting run at when TVB is turned on. Or actually, it's not even TVB being turned on when the CPU is allowed to boost to 6 gigahertz, because TVB is still on if you limit the boost to 5.7 in the OS, right? Like, that just blocks the single core boost. It doesn't, like, TVB also has a multi-core component. That's not blocked on these servers. I did also ask them if they wouldn't, like, consider limiting, like, to 5.5 gigahertz or something, and they told me that on the timescales that it takes for these CPUs to fail, that it's like, like, do you really want to, like, you know, if with the, like, fully unlimited, the CPUs fail in 1 to 2 months, like, more 5.7 gigahertz limit, they fail in, like, 3 to 4, and significantly less often, like, 5% of them fail. So, like... if you limit them to 5.5 and they fail in like a year, well, these servers get replaced every 1 to 2 years anyway. So at that point, it's just like, you know, you're not gonna, like, that's not gonna give you very useful, like, reliability data because they're gonna be replacing them anyway. Yeah, like, as part of the leasing contract that they have, like, they're not paying for the hardware getting replaced, so it's just annoying that at this point, the data center that they're leasing from has run out of replacement i9s. So, yeah, so they're just, like, basically they came to the conclusion that, like, 5.7 is good enough for the, like, gives them good enough reliability, and they're not gonna limit them more than that. Yeah, so I really think that this is just, like, the voltage that these servers end up running at. I also asked about, like, if they have any, like, 13th gen CPUs in, like, you know, if they've been running any 13th gen CPUs. And I was told that nobody in Minecraft is using 13900Ks anymore, but I am aware of a 13900 non-K also failing. So I'm going to assume that they killed all of those. Or something. Or maybe they were just too unstable. I don't know. But, like, apparently they don't use any more 13900. Like the person that's leasing these 14900Ks, they don't run any 13900Ks. And, like, they know other people who run Minecraft servers, and they apparently all, like, nobody's running 13th gen anymore. No details as to why, but I can, you know, we can guess. And on the 12th gen side of things, the quote I got is, I am unaware of a single 12900K that has failed, and there are several running for years straight in Minecraft. So 12900Ks really, like, haven't given them any issues whatsoever. So yeah, super interesting. Because these are, like, running low temperatures, high voltages still, right? But again, like, Intel's TVB system, like, runs high voltages. Like, that's the whole reason why Intel even extended the vid table to 1.72 volts. And on that note, this is not a safe voltage. Okay? This is not safe. This isn't in the Intel documentation because this is a good idea and should ever be applied to an Intel CPU. This is in the Intel documentation because with 6th gen, the vid table literally stopped at 1.52 volts, right? So what this meant was if your Intel CPU, like if Intel wanted to ship a CPU with, say, a vid of 1.53 volts, they couldn't. It was physically impossible, because if the CPU tried to request 1.53 volts from the voltage regulator on the motherboard, there wasn't a 8-bit vid code to describe 1.53 volts. So the way Intel's vid works is it's an 8-bit number that is sent by the CPU to the voltage regulator. And the typical range is from 0.55 up to 1.52. That's all of the values of vid that you can describe, and it goes in 5 millivolt increments, if I remember correctly. So if you want to describe a voltage of less than 0.55, you can't. And if you want to describe something higher than 1.52, you also can't, because there literally isn't a combination of ones and zeros to describe a value bigger than 1.52. So with 8th gen, Intel used their foresight and basically came to the conclusion, sometime in the future, we might make a CPU that'll need more than 1.52 volts. Like maybe a 9900KS or maybe the 8086K or 10900. Actually, there wasn't a 10900KS, but like some future 14 nanometer CPU, we might need more than 1.52 volts because we decide to push the single core boost too high or something. And we need more than 1.52. So the solution they came up with is, we just add an offset to it. And that offset maxes out at 200 millivolts. And 1.52 volts plus 200 millivolts is 1.72 volts. So now Intel is capable of describing voltages up to 1.72 volts. And as far as I know, they never used that capability until we got to the 14900KS, where you can get CPUs where there are 14900KS chips out there where the vid is 1.549 volts for 6.2 gigahertz, which you will notice doesn't fit into the old 1.52 volt vid standard. Also, I just realized that Intel's vid tables don't go in steps of 5 millivolts. Yeah, I don't think they do. Oh, wait, no, because you have... Let me just pull up the Igor's Lab article. Oh, wait, no, it is in 5 millivolt increments. Well, 1503, 1498, 1493, 1488. Yeah, so I do remember correctly. It is 5 millivolt steps. Man, I was really worried for a moment there where it's wait a minute, did I say something wrong? But no, it is 5 millivolt steps. It's just weirdly shifted upwards. I guess they just ship all the 14, they might just be shipping these CPUs with a permanent positive offset. Or it might be some weirdness with the Asus motherboards reading them. But yeah, because I think I heard that ASRock motherboards read different vids, by a couple millivolts different vids than Asus boards. So not sure what's up with that, but they do have that offset option, so they can shift it around a bit. But yeah, so that's the main thing is you can get a 14900KS, which will request more than 1.52 volts, and if you tried to use the old voltage regulator standard from 6th gen Intel, well, that would physically not be possible. Right, that CPU literally couldn't make that voltage request because there was simply no way to describe it. So Intel extended the voltage tables up to 1.72 volts. If you actually ran your CPU at 1.72 volts, it will very rapidly degrade. Okay? If your CPU is anything, if your CPU is at positive temperatures, as in, CPU operating temperature is greater than 0 degrees Celsius, it will very rapidly degrade at 1.72 volts. Do not apply 1.72 volts. You might remember I made a video showing how Gigabyte put out an Intel baseline BIOS thing where the CPU would end up at 1.6 volts. That got pulled by Intel. Apparently somebody from Intel found it, saw that video, and that BIOS that Gigabyte put out where it would go up to those insane voltages, that got removed. because that is just no. Um, so, yeah, so this number here is like a hypothetical vid request that Intel could make if Intel wanted to. But Intel doesn't want your CPU to disintegrate within like a week, so they won't do that. They want your CPU to degrade in like 6 months. Which is why the vid tables stop at like 1.5-ish for the i9s. That's still my personal theory on why we're seeing so much degradation, is like they really like overshot it with the maximum safe vid. Either from the perspective of like, because the thing is, we have already heard about TV, like the patches to TVB to like lower the temperature limits, or like some motherboards were like boosting the TVB temperature limits. And so Intel's like done stuff about that, because as off the top of my head, TVB is literally not supposed to kick in unless the CPU is TVB is supposed to disable if the CPU is above 70 degrees Celsius. There are motherboards, like there are BIOS, like old BIOSes for Z790 motherboards where you can get like the full 6 gigahertz single core boost all the way up to like 100 degrees Celsius. So those like that is violating how TVB is supposed to work. Now, the thing is, like, these servers that I'm telling you about here, well, they don't run at above 70, right? Like, even running a single core Cinebench here, this is like 66 degrees Celsius. And then the quote, from the person leasing these systems is that they usually run at like 50 to 60 degrees. Now, they could be lying to me. I don't know why they would be, because they're locked into a 1-year, like they're locked into a contract for these CPUs anyway. So, I don't know. I'm not sure what the motivation behind lying to me about the operating temperatures would be. Or like they could be lying, right? They could have not been paying that close attention to the operating temperatures of these systems, though I do trust that the max temperature has never gone above 83 degrees, because that seems like your monitoring software probably keeps pretty decent track of a maximum operating temperature, right? Average temperature, that might be a bit more wishy-washy, but like never went above 83 degrees. So these things aren't going to be running super hot. And yet they're like failing really, really fast. So I think so a way to look at it is so my theory is like either TVB, like you can look, because the thing is, the lower your operating temperature, the higher voltages you can run safely, right? That's why if you're on liquid nitrogen, you can get away with voltages like 1.72 volts, right? But yeah, if you're on like air cooling or water cooling, I'm wondering is like, oh, are they gonna like lower the TVB limits to like 50 degrees Celsius or something? Because then it's like, yeah, because that is the thing. Like, as you lower the as you lower the temperature, the higher, like, the voltage does get safer. But I don't know by how much for how big of a temperature step. So yeah, though also Intel is turning like a lot of the gaming motherboards. Though the thing is, this isn't a gaming motherboard. This has all the one thing we can't check is if this had the CEP turned on, but like they didn't even flip the unlimited current bit. They're not messing with they're not doing anything weird with the AC/DC load line. So I'm gonna assume that this is actually like properly this has CEP turned on. Just because I would assume it would actually be more work for Supermicro to go into the BIOS and turn it off. I would assume it's turned on by default from Intel, and then like it's something you actually have to like choose to disable when you're making your own BIOS. So yeah, so I'm still in camp like, oh, they're going to have to do something about the operating voltages, either by, because like technically if you just set the TVB limit really low temperature, right, like that'll lower the voltages because the CPU will never reach 6 gigahertz. And if the CPU never tries to boost to 6 gigahertz, it'll never use the insanely high vid voltage. Problem solved. Just set the TVB limit to like 0 degrees Celsius. Won't see what like chip won't try to request 1.5 volts anymore. You know, you get one of these potatoes over here, and it won't try to kill itself. If the temperature limit for that part of the vid table is like literally below room temperature. So yeah. So anyway, also like yeah, this is not safe. This isn't some like oh this is a good idea. It's a terrible idea, and also it's been in the Intel docs literally since 8th gen, right? This is like Intel 8th gen, 9th gen documentation. Like, it would be a weird coincidence for 14 nanometer and like Intel 7 CPUs to have the same max voltage limit. You know, just saying. Very different manufacturing process. Kind of suspicious that they would have the same same voltage limit. Now, you could also argue that Intel just wasn't bothered to test higher voltages for safety, but 6th gen, like you go look at 6th gen, which is also 14 nanometer, and that's 1.52. And funnily enough, if you check the Sandy Bridge documentation, which is 32 nanometer, that's also 1.52. But then I think X58 actually goes to like 1.65, or something like that, even though that has both 45 nanometer and 32 nanometer. And the 32 nanometer chips, as far as I know, actually degrade at voltages that high. So, yeah. The voltage numbers in Intel's documentation are not like they're not for the motherboard vendors. They're not for well, they are for the motherboard vendors because basically you need to like your voltage regulator needs to be able to support this vid request. But Intel is never going to send that vid request if the motherboard is working correctly. Like if you do what Gigabyte did on that Intel baseline BIOS mess that they made and set the AC load line to 1.7 milliohms, then yeah, the CPU is going to make vid requests that reach into like the 1.6 volt range, but that's not working correctly, right? Like that's literally like, because Gigabyte, what they did is they applied the 1.7 milliohm 1.7 milliohm AC load line to a 125 watt CPU when this load line is only for the 35 watt parts. So, yeah, like, so just don't, and like the thing is like even Sandy Bridge, you can break Sandy Bridge CPUs with 1.52 volts. And I know from experience because I've done it. You can also degrade... Oh, also that 1.52 volts is in the data sheet for 3rd gen Intel and 4th gen Intel. So, actually, no, 4th gen Intel doesn't have a core voltage operating range in it, or some... I have an operating... Like, it doesn't have a core voltage, like, rating, because the voltage regulator for that is internal to the CPU. It's not on the motherboard. So the motherboard doesn't the motherboard doesn't need to know what the CPU is doing with its voltage anymore. But with like 13th gen, 14th gen, 12th gen, well, everything after 6th gen doesn't have an integrated voltage regulator for vCore. So the motherboard needs to know what to do when the CPU sends a vid request, and that's why this exists. Anyway, so yeah, I just found this like whole like discussion I had about these Minecraft servers really interesting. So I figured I'd share it with you. Because, yeah, like these things, these are about as like single usage systems as you're going to get, right? So you have like a very, very controlled operating environment, right? This isn't some like gaming system where Gigabyte is turning off all the current limits or Asus is turning off all the current limits and messing with the AC/DC load lines and doing whatever else. This is about as Intel spec as the motherboard configuration gets. The temperatures, if they are to be believed, were very, like the operating temperatures are very reasonable. The system was never really getting loaded very heavily because, again, it was running Minecraft servers, which just aren't that heavy. And yet, these CPUs were degrading very rapidly. Also, these were running Linux, as far as I know, not Windows. So, yeah. So I just found this really interesting because this is like this is a very controlled setup, relatively speaking. It's a lot of systems running the same settings, and yeah, they were failing very, very, very quickly. Um, and you can't like this isn't like, well, there's the no current limit. It's like, well, there's the like I guess you could go like, well, the AC/DC load line are very high, but then it's like, then why is Intel? I mean, to be fair, I've just complained about how Intel has 1.72 volts in their documentation. Um, but like then you have these current limits, and you know we trust all of those. um, and then you have like so the load line limits, and as far as I know, most of the patches that Intel has been pushing are actually pushing the AC/DC load line back up to 1.1 milliohms. So it's like seems to me like I haven't looked at the latest patch from Intel yet, but it seems to me that like Intel does like fully stand by this AC/DC load line thing, like this AC/DC load line setting. So like, um, yeah, um, I just found this like super super interesting. Because this is like yeah, like this is one system where it's like I can't even really like I can't really see anything other than like the voltages, but the voltages like anything to complain about the about except the voltages, but the voltages are behaving as Intel intended as far as I know, unless even this super micro board has a bug where TVB works at temperatures that it shouldn't be working at. Because there was, as far as I know, there was a microcode patch to deal with some kind of temperature issue with thermal velocity boost, but I'm not sure if that is because the motherboard manufacturers were like tweaking TVB and that was like Intel's way of like fighting back against them. Kind of like how motherboard manufacturers were unlocking AVX 512 or non-K overclocking, and then Intel puts out microcode to block that kind of stuff. Um, Actually, it's not always microcode. Sometimes it's like, oh, no, no, I think it's microcode, and sometimes it's management engine updates as well. Um, anyway, so yeah, ultimately, like, yeah. So just looking at this, was just interesting to me because it's like a very reference, if you will, system, and insanely high failure rate, right? Like 1 or 2 months for like 30% of CPUs to die. Like that is insanely fast. That is so fast that like you wouldn't really like if you wanted to test this in a lab, it wouldn't even take that long, right? Like you could buy 100 chips or 10 and you'd probably end up with 3 dead ones in like 2 months of running a Minecraft like of running Minecraft server software, which is like like that's just insane to me. That like it's so fast. Now, admittedly, this is 100% load all day, every day, which is like the big difference between these Minecraft servers and regular users. Right, regular users do other things. It's not exactly like, but and they're also like these Minecraft servers are very memory heavy, but yeah, super interesting. And also, actually, on the note of being super like very memory heavy, that memory isn't going very fast. Okay, like I mentioned earlier, it is DDR5 3600. No, it just says unlimited there, but that's not what I wanted. Okay, well, we can just look at the screenshot, I guess. Because it does say, see, memory, 128 gigs, clock, 1800 megahertz. So that's 3600 mega transfers per second. So yeah, like the memory's not going super fast. It does have ECC. And the ECC is not detecting any like memory errors, right? Because you can just get like if you have ECC memory, you can just check for ECC like memory errors, and it's not getting any like main memory errors. It's getting like internal CPU memory errors, which is the L3 cache basically. Or I guess it could be even like the L2, L1, that kind of thing. But I was hoping to find the ECC. Ah, yeah, there we go. So physical memory has ECC. So this memory speed here, that's actually for the actual parts. I think. I've never really dug into hardware info reports before. But the thing is, like, DDR5 4800, I don't, like, I think that's literally just the memory sticks. Because, like, SK Hynix makes memory sticks that, like, will go faster than what Intel supports. Yeah, so it's literally just a 4800 stick, which is not surprising at all. I don't actually think there's any CPUs that... Actually, maybe the EPIC CPUs from AMD, because the memory controller on those is quite different from the regular 7000 chips. Actually, no, because these aren't RDIMMs. These are UDIMMs. So you can't use these with EPIC. Or even Threadripper. Yeah, so there's literally no CPU. Oh, if you run one... Oh, wait, no. If you run one of these sticks per memory channel, you can probably run them at 4800. If you run two of these per channel, you can't. But anyway, so that's it for this video. Oh, no, it's an hour long. Hopefully you found it as interesting as I did. Because, yeah, that'll be it. I've said everything I want to say, I think. So hopefully you found it interesting, because this isn't useful. It's just, I found this interesting and I wanted to share. So, yeah, that's it. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store, where there's like shirts and hoodies and posters and, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it for the video. So thank you for watching and goodbye.